Hey guys, my name is Shreyas and welcome to Simple Chemistry. We've been talking about a lot of vague concepts like the electromagnetic spectrum and the dual nature of matter and light and things of that nature. And you might be wondering, how does this all tie together when we talk about the atom? Well, this video we're going to really tie everything in together and you can understand why we discussed the previous topics that we learned before in order to explain what's going on here. So let's get right into it. So a hydrogen atom consists of one proton, which is a positively charged particle, and one electron, which is a negatively charged particle. Okay, and the generic diagram of that is this. So you have the proton in the middle, which has a positive charge, and then electron on the outside, just kind of circling around, which has a negative charge. Okay. Now, when hydrogen gas is excited, meaning given energy, and then the energy is released, only light with specific wavelengths are emitted. So basically what's happening in this diagram here is we have a hydrogen gas in here, and we're using a source of electric potential in order to give it energy. What happens is that the hydrogen atoms essentially are getting excited and they're going to get energy, and then that energy is going to be released. When that energy is released, it's going to give off light. The light is put through a prism, and when it's put through a prism and the waves are separated, you notice that only light with specific wavelengths are emitted. If you look here, you might be able to see the different colors, purple, blue, green, and yellow. So only these four lights with specific wavelengths are emitted. So this is called a line spectrum. Okay. And actually, all compounds and all elements have different line spectrums, depending on their what the element is. Okay, but you're never going to see what is called a continuous spectrum. It's called a line spectrum. Like in comparison, that we have a continuous spectrum. This is probably something you're familiar with. So you know what a rainbow is. Whenever you take you've probably seen a rainbow, or whenever you just take a prism and you just shine it in the sunlight, you'll see that all the colors of the rainbow, of the visible spectrum essentially, are being displayed. So that's the difference between a continuous spectrum and a line spectrum. Okay, and also understand that a line spectrum for every compound and every element is slightly different. So what's the significance of a line spectrum? Okay, so again, like I mentioned, all elements and compounds have unique line spectrums which are different from each other. The line spectrum is actually a huge clue into discovering the structure of the atom. Why is that? So this is Bohr's hydrogen atom model, and this is revolutionary. When this line spectrum thing, which you've talked about, is going to make sense when you look at this. So Bohr thought that, okay, for a hydrogen atom, you're going to have, again, the proton, but then you're also going to have these energy levels. Okay, so if you look at the first ring and then the second ring, the first ring here, the second ring here, the third ring here, and the fourth ring here, are all what he called energy levels. Let me write that down for you. Okay, so they go from in to out. The energy level closest to the nucleus is going to be energy level 1, and then 2, then 3, then 4, as you go out. And the energy levels have more and more energy. So energy level 1 is not going to have as much energy as energy level 4. The farther you go out, the more energy you're seeing. So what Bohr was thinking was this was the model for the atom. Just like how you can think of the solar system and you think of planets, you might be thinking like, oh, you have the sun and then electrons, planets going around. In the same sense, Bohr thought that the atom was that. Why did he think that this was the model of the atom? Thinking back to Rutherford's nuclear atom, Rutherford just thought that you had the nucleus, and then you just had this, this electrons just dispersed like this, just dispersed. But in comparison, Bohr thought that there's this planetary model. Okay, so why did he think that? Well, the reason for that is it goes back to this this atomic spectrum here. So basically, what Bohr was thinking is that whenever you're giving these the hydrogen atoms within this tube energy, what's happening on the atomic level is that you have an electron. Let's draw an electron. Let's say an electron here. So this electron is in the what we call the ground state. Let me write that down. That's another important term. Okay, ground state means it has the least amount of energy possible. Okay, so it's like you can think of it like the very, very lowest energy that it can possibly have. It's in the ground state. And then here, whenever we start to add energy, the electron is going to shoot up into other energy levels. So let's say it goes to energy level 3 like this. Or no, yes, from energy level 1 to energy level 3. Because it's getting energy, it's the electron's getting energy from the electric potential. It's able to climb these energy levels. Again, like I said, each energy level has more and more energy. So as it climbs up, it's going to get more energy, and it's getting that from the source of energy here. Then what's happening is that after that energy source is gone, it's going to go back down to the first the ground state. Okay, so you can think of it as a cycle. It's getting energy, going up energy levels, and then coming back down like this. So whenever that happens, that release of energy, let's say energy is being released, right? Because in order to go back down, the energy needs to be released. So whenever it's being released, that energy we're seeing released is essentially just electromagnetic radiation. So now this is how everything's going to start tie together. I'm going to tie together. Let's look at this. So again, the electron is in the ground state. It's going to move up in energy levels, therefore gain energy because of the source of energy here. Then it's going to come back down. Whenever it comes back down, it needs to release energy. That energy is going to be released as electromagnetic radiation. And whenever, remember from the other video, we talked about how electromagnetic radiation can be thought of as a wave or as a stream of particles. So you can think of the energy being released as either a wave or a photon. Both, okay? So that energy is being released, and whenever that energy is being released, but since the energy differences between each energy level is different, so let's say from the difference in energy from energy level 2 to energy level 1 is different from the difference in drop. Sorry, let me rephrase that. Let's say an electron goes to the second energy level from the first and then comes back down. It's going to release not as much energy as when it goes to, let's say, the fourth energy level and then comes back down. Those are all very specific energies. So therefore, we're saying the energy is quantized. That's how we're getting the quantization of energy. And then whenever that energy is being released, that's how we're seeing these specific line spectrums. Because since each energy level drop is giving a different amount of energy, that energy is going to result in different waves. Okay, so everything tying down together. Okay, let me run through the process quickly again, just to recap. An electron is going to be get energy in order to go up in energy levels. That's coming back down. It's being released as electromagnetic radiation, that energy, which whenever it goes back down to the ground state, it can either be released as a wave or as a photon. You can think of it as both. This is showing that energy is quantized because the electron can go to, let's say, 1 to 2 or 1 to 3 or 2 to 3 or 3 to 4. Those are all different energy being released, and that energy being released is going to result in different waves with different wavelengths, and therefore we're getting this atomic spectrum. And this happens not just for hydrogen, but for every single atom. Okay, so that's how everything ties in together. Okay, so this equation, Bohr's equation for the hydrogen atom, shows how much energy is in every single wavelength. Okay, so what basically this is saying, no, what am I not saying? Every wavelength, every energy level. You can use this equation to see how much energy an electron will have within the hydrogen atom at a specific energy level. So basically, you're going to multiply negative 2.178. The reason why the energy is negative is just physics reasons. Don't worry about it. Just so 2.178 times 10 to the minus 18 joules times z squared. Z is the atomic number. At least for hydrogen, just assume that this is just 1. We're going to be talking about what atomic number is later. What you really need to focus on is n squared. So n is the energy level. So if you're talking about the third energy level, you just put 3 here, okay? Or if you're fourth, you just put 4. So you just multiply negative 2.178 times 1 over that number and then squared. Very easy. And that's how you get the energy for a specific energy level. So let's look at a problem which kind of ties all this in together. Calculate the amount of energy that is released when an electron in a hydrogen atom travels to energy level 3 to the ground state. Then find that wavelength. So essentially what we're seeing is there's an electron in energy level 3. So let's say 1, 2, 3. So let's say, yeah, 3. This is, I already drew this. So 1, 2, 3. It's going up to the third energy level. It's coming back down. And it's releasing energy. So the question is asking us first, how much energy is being released? So all we have to do is use this equation here and see how much energy an electron has in the third energy level, because that's where it's starting at, and then see how much energy the electron has is in energy level 1, and subtract that differences in order to calculate what the drop in energy is going to be, essentially how much energy is going to be released. Okay, so let's go ahead and do that. So let's say, I'm just saying this is for energy level 1. So E equals negative 2.178 joules. Oh, sorry, times 10 to the minus 18th joules. Times 1, because I just said, here, just assume that Z is 1. We're going to be talking about what that means later. Over, and then since you're talking about energy level 1, it's 1 squared. So this is just going to be this number times 1 over 1 squared, which is just going to be negative 2.178 times 10 to the minus 18 joules. Okay, so this number is saying that in a electron in energy level 1 is going to have this much energy. Now let's see how much energy electron in energy level 3 is going to have. So again, E equals negative 2.178 times 10 to the minus 18 joules over 1 over, and then 3, so that's going to be, since it's energy level 3 squared, so that's going to be this number, 1 over 3 squared is just 9, So let's go ahead and calculate this using a calculator. Negative 2.178 times 10 to the minus 18 times 1 divided by 9. It's going to equal this. So it's just negative 2.42 times 10 to the minus 19 joules. Okay, so then from here, what we have to do is we're going to have to take these numbers and just subtract them in order to calculate the energy difference. So we just take negative 2.42. Okay, because we're seeing the energy level drop from energy level 3 to energy level 1. So we're going to have to take this number and then see, we're going from energy level 3 to energy level 1, right? So what we're going to have to do is take this number, so negative 2.42 times 10 to the minus 19, and subtract that from negative 2.178 times 10 to the minus 18. Okay, because we're going this way, from 3 to 1. So negative 2.42 times 2.42 negative times 10 to the minus 19 and then subtract negative 2.178 times 10 to the minus 18. So we're getting this. Okay, if you subtracted, if you did negative 2.178 minus negative 2.42, you're getting the wrong answer. Understand that the reason why I'm subtracting negative 2.42 and starting negative 2.42 times 10 to the minus 19 minus negative 2.178 is because we're going from energy level 3 to energy level 1. Okay, very critical. So we're getting this. So the energy which is being released is 1.936 times 10 to the minus 18. So let's write that down. Okay, and this is being emitted as, you can either think of it as a wave or as a photon. Okay, same thing. And this is showing that energy is being quantized because if you wanted to go from energy level 3 to energy level 1, only negative 1.936 times 10 to the minus 18 joules can be released. There's no discrepancy there, okay? You couldn't get negative 1.95 times 10 to the minus 18 joules doing that. So that's how it's showing how energy is quantized, you know? Okay, so anyways, so then it's asking you to find the wavelength. So when this energy is being released, it's being released as, you can either think of it as a wave or a photon. So now the question is asking us to find the wavelength of that wave or photon, whichever way you want to think about it. So we're going to have to use this equation here. Remember, we said delta E equals NHV. So we have the energy, which is 1.936 times 10 to the minus 18. And then this is, the number of photons is just 1 because that's kind of important. Whenever you're seeing that drop in energy levels from 3 to 1, it's just 1 photon which is being emitted, so we know that's just 1. Times Planck's constant, 6.6262 times 10 to the minus 34th joules times second. And then from there we can get the frequency, and then from the frequency we can calculate the wavelength. I know this is a lot of work, but I just went ahead and did a hard problem so that you can get all the easy problems, So .936 times 10 to the minus 18 divided by 1 times 6.6262 times 10 to the 34, 10 to the minus 34th. I'm getting this. Okay, and then change that to exponential notation. So getting here. So just basically 2.922 times 10 to the 15th hertz. Okay? And finally, from here, can we use... See, everything's starting to tie together. You're able to understand the electromagnetic radiation. You're able to see why you need to understand what the wave is. Like, everything's starting to tie together here. This is really where, like, everything comes together. You have to understand all the topics from the previous videos to be able to do this. So here we have the frequency of the photon which is being released, or essentially just the wave. It's the same thing. You can think of it as both. So from here, let's go ahead and calculate the wavelength of that wave. So we know that the wavelength times the frequency of any wave equals the speed of light, which is 2.998 times 10 to the 8th meters per second. So we're going to have to divide that by the frequency we have here, so 2.99922, sorry, times 10 to the 15th hertz. We're going to be left with, let's see here, okay, we're left with this. So, oh crap, why did I speak that? Okay, so we're just left with 1.026 times 10 to the minus 7 meters. Okay, so that is, well, I know that was a lot of work, but yeah, that is the wavelength of the wave that is being released when a electron in the hydrogen atom is going from energy level 3 to energy level 1. So just to put this conceptually, let's review this. We have an electron in energy level 1, it's being raised to energy level 3, and then it's being dropped back down. Whenever that's being dropped back down, a photon or a wave is being released in electromagnetic radiation. As electromagnetic radiation, it's essentially energy, and from that you're able to see the line spectrum, because every different drop in energy level is going to give a separate wave with which have different wavelengths. We use that information where we use the Bohr's equation for the hydrogen atom in order to calculate the difference in energy levels, in order to see how much energy is going to be released whenever the electron goes from energy level 3 to energy level 1. And then we use that information to use the two equations we learned about waves in the previous video, in previous lessons, to calculate first not only the frequency of that wave, but also the wavelength. Okay. Last note, this is I want you to just take this. An absorption spectrum is a spectrum of what an atom will absorb, while an emission spectrum is in the spectrum of what an atom will emit. So an absorption spectrum would be all the energies of the, if you take an atom and you see all the energies of what an atom will accept in order to go up in energy levels, so all the electrons going up to higher energy levels, the wavelengths of all that energy is the absorption spectrum, while the emission spectrum is what the spectrum of what an atom will emit. So when we're looking at here, this is the emission spectrum, because we're seeing the energy of when the electrons come back down. So absorption spectrum is when all the energies of the waves for the electron to go up, and the emission spectrum is all the lines of the energies of the waves when the electron comes back down and energy is being released. And a spectrometer is a machine which helps determine the absorption and emission spectrums of different elements and compounds. Okay, so I hope everything has come together. Obviously, if you're kind of weak on a topic, just go ahead and review that. But I hope you can finally understand how all these things tie together in order to create this concept, Bohr's atom. In the next video, we're going to realize that not even Bohr's atom is correct. It gets a little bit more complicated than this. But don't be scared. I'm going to explain it to you, and you're going to be fine. Bohr's atom and atomic spectra is as simple as that.